Hi and welcome. So on the last video we start to solve this example 2.24 and we have just drawn this illustration of this simple 2x planar robot. So don't misunderstood the meaning of 2x with the meaning of the degree of freedom of this robot. Well, it has 2 degrees of freedom because this base is fixed and we only got motions on this joint and on this joint. So being a 2x planar robot and being a 2 degrees of freedom right here is only coincidence. Okay, so we start um, to use all that we have learned from the theory of Dynavit-Hartenberg. So this theory, this procedure is used in robot arms with any number of links and joints. And as I already have said to you, as I already told to you, is the standard way to represent a robot. So again, I think this is already the fourth or the third video about DH. And about now, you know that in order to solve this type of problem, this type of exercise, first we need to assign reference frames to each joint of the robot. So we right here on the last video we assign this axis x1, x0, x1, z0, z1 to each joint right here, and this way we are turning this into frames, and this way we got reference to be capable of track the motion of this robot. And okay, and for that we also use this universal reference frame. As I said, with this universal reference frame, further we will see that because of this we are capable of use some type of metric, let's say inches or centimeters. In this way we are able to measure in terms of space. Okay, and also something important, and we need to pay attention. We do not assign this axis in any way. We need to follow a procedure which tells to us how to the right way to assign this axis. Okay, and assign this axis and turn it these joints into frames, into reference frames is just the first step. And the second step, actually let me correct me, is something that maybe committing a misunderstood. Just the order that we are using to transform from one local reference frame to the other. Uh, yes, we use a sequence of steps. So again, the first step is to assign reference frame to each joint. So assign this axis and assign this axis on each joint. And again, we just assign the x-axis and the z-axis. DH does not use the y-axis. And I don't know if on the last videos, on the two last videos, have been said that this is the second step, but this general procedure is already the third step. So within this general procedure, which that we use to transform from one reference frame, local reference frame to the other, so from one joint to the next joint, is this third step. So right here actually is just some nomenclatures and descriptions, for example, of how we can um, assign the common normal, where we need to take a reference to place each of these elements on the right place in the right way when we are solving some problem. And we start by drawing this problem like right here. So the common normal, as we already saw, so it can be the shortest distance of two scale lines or the length of a link. So right here we got this scale line and this other scale line, and the shortest distance between these lines we assign the common normal, or we can say that the common normal is the length of this link. Okay, and I'm saying that this is the third step, but it can be the second step. What is important is that this is the procedure, general procedure. Okay, and we write the procedure, we write the four motions. So this that I'm calling the third step is a procedure of four motions, a sequence of four motions that we need to do in order to accomplish a transformation from one frame to the other or between frames. So this is a sequence of four motions. And we need to do the sequence on this correct order. Okay, so let me just copy this illustration. And now, as I said, let's try to illustrate this these motions on this draw. Okay, so let's first try to write a transformation equation. So pretty much a transformation equation is always the generic solution for a robot with any number of degrees of freedom. So let me change this color, and remember from previous lessons that we can substitute this universal reference frame to a frame that we call the reference of the robot. So instead of use U, we will use R. And right here, Y is just to complete the reference. Of these components on the 3D plan, on the 3D space. Because the robot is localized, is placed on the 3D space. Okay. And now this is sometimes we see as being the reference of number 1, sometimes as reference frame number 0. So right here is the number 0. Just 0. So let me write reference 0, reference frame of number 0. And reference frame of number 1. And right here is most common, is most known and common as the hand, reference frame of the hand. Okay. And if the base is fixed, so the base is fixed. Also this axis, this link is fixed. The link of the base is fixed. So it won't count on the transformation equation. So let's write a transformation equation. Which again represent the motion of this robot, and again is tracking the motion. It tells to us how um, this motion are occurring in space, since this z frame, zero frame, to the hand of the robot, which is the end effector. Again, this is the end effector. So we can write that again. Let's write in parts. So the first transformation that we can identify is the one that tells to us the desired total transformation. So the first transformation that we can write is the total transformation. And the total transformation is the transformation that we made from the first frame to the last frame. So as I'm writing right here, if the base is fixed and also the link is fixed, uh, generally we used to write that this total transformation is a transformation of the end effector of the frame H in relation to the frame R. But as R is the frame that is fixed and it doesn't have any motion, so it won't count right here on this transformation equation. So we start from the frame 0, which it does have motion. So what we can write is a transformation of the frame H in relation to the frame 0. So is a transformation of the hand of the robot in relation to the frame 0. And this is the total transformation. And this is equal. And remember that we always use a frame as a reference to the next frame. So one frame becomes a reference on the operation of transformation. So right here we will start since the end effector. So our second transformation that we can write is a transformation in relation to this frame. So a transformation in relation to the 8th frame. Sorry, a transformation of the H frame in relation to the frame of number 1. So frame 1 is a reference frame to the frame H. So transformation of the frame H in relation to the frame 1. And we multiply these transformations to get our total transformation. Okay, and now we can write a third transformation. So now the frame 0, the reference frame 0 is a reference. The frame 0 is a reference frame to the frame 1. So we write that a transformation of the frame 1 in relation to the frame 0. And again, we usually would write a last transformation, which will be a transformation of this frame 0, in relation to the frame R. But as this link, it doesn't have motion, we don't write a transformation for it. Okay, now let me again copy this illustration, and we will start to apply the 4 motions. So the first motion is a rotation about the z-axis, an angle of theta 1 to make x0 in parallel with x1. Okay, so let's do this. As you can see, theta 1 is right here. And let me decouple this link. And now we need to rotate till x0 got in parallel with x1. Maybe we can do this. And this way we are doing x0 in parallel with x1. Okay. As you can see now, they are in parallel. Okay. And let's also already work on its matrix. So remember that for a transformation using DH, we got a generic solution, a generic matrix, which represent this transformation. So we already has calculated this transformation. And right here, since x0 and x1 are in the same plane, now that they are in parallel, the translation d along the z0 axis is 0. And why this? If you can notice right here, z1 and z0, so z0 pointing to here, and z1 on the same plane is right here. Let me change the color. Z1 is right here, its axis is right here, and Z0 is right here. And this because we had rotated the Z0 axis angle of theta 1 to become in parallel with the axis x1. So x0 got in parallel with x1. And right here, again, the second motion is a translation along the zn axis, a distance of d, to make xn collinear with x n plus 1. Okay, and let me also try to represent what this second motion of translation we will do. So if x1 it was right here and x0 right here, and this is because of the first motion of rotation, so they became in parallel because x1 was this on this way and x0, let's say about this way, and after rotate they become in parallel this way. And a translation is to bring them together on the same plane. And if we pass a dashed line right here, something like that, yeah, I got an error right here because it is out of scale. But in theory, x0 and x1 are on the same plane, and because of this distance is 0. Okay, so let's get back on the matrix. So right here, looking at the elements of the matrix, you can see that it's made of sine and cosine components. So we need to look at this this figure, this illustration, and using the axis of the frames, we need to decompose this axis um, sine and cosine components, so we can substitute right here on the elements of the matrix, and also doing the analysis of the motions that we are doing. Uh, about the second motion, which says that since x0 and x1 are in the same plane, so a translation d along the z0 axis is 0. If you can notice, z0 is right here. Let me again change the color. So z0 is right here, and z1 is right here. Right here is the axis of z0. Right here is the axis of z1. So z0 is on this way, and as I already has draw it right here, z0 and z1. So we doesn't need to do a translation because they are already on the same plane, and because of this we said that the distance is 0. So I will let this right here. Okay, and let me borrow this right here. Actually, if you can notice, on the first motion, it says that we are rotating an angle of theta 1, and it does not specify a exact value for this theta. So just like the solution of the book, so the book, it provides a solution which is a generic solution. So it's a solution that solves for any value of theta. But now, as I said, right here we need to do this analysis. If these axes, they become collinear, so we don't have a component for cosine. So right here, if they are collinear, that means that cosine right here is 0. And this is something that we can verify after the third motion. So actually, first we need to do this third motion, which is translate along the already rotated x0 axis a distance of a1, which is our common normal. So if we translate a distance of A1. So this way. So now we are bringing the 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 origins. Actually, we are bringing their origins together and making them collinear. And actually, before we be able to substitute these elements on this matrix, let's see the fourth and last motion, which is um, it says that since the z0 and z1 axes are in parallel, the necessary rotation alpha about x1 axis is 0. So right here, alpha is 0. Let me change this color, maybe green. So alpha is 0. And also, let me place right here a distance of the common normal, A1. Okay, and now we can, so we don't have components also for data, and now we can substitute on the matrix. Okay, any component is sorry, the x's, they are not decomposed in any component. The x and z axes are not decomposed in any component. Okay, and with that being said, we know that cosine of 0 is equal 1 and sine of 0 is equal 0. Okay, so the rotation about the alpha, the rotation alpha about the x1 axis is 0. So alpha is 0. So cosine of 0 is 1. And sine of 0 is 0. Sine of 0 is 0. Right here too, sine of 0 will cancel all these elements, and cosine of 0 is 1. And again, we can use a matrix in a way that we can solve for all values of the data, since the value of data it was not specified. And D is also 0. Right here. The translation D along the z-axis is 0. So right here D is equal 0. Okay, and this is for this transformation from the frame 1 to the frame 0. Which is, we'll use the notation A, so A1. Okay, and this is also solves for the other transformation. So this is also solves for the transformation in relation of the H frame in relation to the frame 1. And we only change this index so we can solve for any value of data. And now we can find the total transformation, which is by multiplying all transformations on the system so let me change this order because the order of the multiplication of the transformation, it matters and affect the final result. And here we can also write that A1 times A2 And now let's use the Octave to evaluate this operation. So again, open up your Octave environment and on the command window type, first of all, type clear all to clean up the Octave's memory. Then type CLC to clean the command window. Now type pkg load and the name of the package that we wanted to load, which is symbolic, because we will use a symbol, the symbol A, A1 and A2. So first of all, we need to type sims, and now we type A1 and A2. Press enter and wait a bit to load the package. Okay, now we just need to enter with the matrices. So let's adapt this one. So let's see. I think I should use the numbers 1 and 2 as symbols because of this index on the sine and cosine component. So let's try again. So I will clean the Octave memory, clean the command window, pkg load symbolic, sims, A1, A2, 1 and 2. And actually, I don't know if this is going to work because we are not passing arguments this time for sine and cosine components, but let's try. Okay, using the numbers 1 and 2 with this command line, command line, it doesn't work. So let's try without these numbers. Okay, let's try to adapt to this matrix. So this is going to be cosine 1 minus sine 1, right here 0, and right here is A1 times cosine 1 sine 1 cosine 1 0 and A1 times sine 1, and this is the matrix A1, and for the matrix A2, I don't know if this is going to work. Right here is C2 cosine of 2 minus sine of 2 0, right here is A2 cosine of 2 sine of 2 cosine of 2 0 A2 times sine of 2, and this is it. Well, I'm not sure if it's going to work, but let's see, let's try. it doesn't work because of this one in index. Well, I will try to solve this, and if it didn't work in Octave, we can do by hand, but yeah, we need to be able to do this using the Octave. Okay, so for now it's all, and we will continue with this on the next video. And hope you understand what I tried to explain. Maybe it was a bit confusing. And again, I will watch this video, and if it does not coming very well, if I miss some part or I explain wrong, I will do a revision and explain again. But that's it. Thank you.